So today, we're going to tackle a really fascinating and, well, kind of counterintuitive idea in the world of artificial intelligence. We're asking, what if the secret to smarter AI isn't about getting bigger, but actually about getting much, much smaller?
Okay, let's just dive right into this, because for years, it's felt like the answer was an obvious yes, right? But is that really the whole story?
I mean, the story in AI has been all about one thing: scale. We hear about these models with hundreds of billions, even trillions of parameters running on these ginormous server farms. The whole philosophy has been super simple. To make it smarter, just build it bigger.
But this is where our story really gets interesting, because we're going to challenge that exact idea. Let's take a look at AI's bigger is better myth.
It turns out there's a whole class of problems where just, throwing more computing power, more data, more parameters at it, it just doesn't work. These giants have a serious Achilles heel.
All right, so let's get specific. Where exactly do these huge models just completely fall apart?
It all boils down to this thing called autoregressive error. Now, the best way to think about this is like building a house of cards. Large language models build their answers one piece at a time. They call these pieces tokens, which are basically just words or even parts of words. If they make one tiny mistake early on, the whole structure they build on top of it just collapses, and the final answer is totally wrong.
And hey, don't just take my word for it. Look at the actual data here. You've got DeepSeek with 671 billion parameters. Think of parameters as all the little knobs the AI can tune to learn. But when it's faced with a really hard Sudoku puzzle, its accuracy is a flat zero. Zilch? Nada. And it's the same story for the other giants on similar logic puzzles. Brute force is failing, big time.
Okay, so if the big guys are failing, what's the alternative? Well, that led researchers to a pretty clever but also really complicated first attempt to crack this thing.
So say hello to the hierarchical reasoning model, or HRM for short. Now, at 27 million parameters, it's way smaller than a giant LLM, but it tries to solve these puzzles with this complex system of two different neural networks that have to work together. So the main thing to get about HRM is just how, well, complicated it is. It's inspired by these super abstract ideas about the human brain. It uses heavy-duty math just to get it to work, and the training process itself, super inefficient. It's a very intricate, very complex machine.
But what if all that complexity was just overkill? What if the real answer was something way, way simpler?
And this, my friends, brings us to the hero of our story, the Tiny Recursive Model, or TRM. The idea here is just beautiful. It uses one single small network, and it works recursively, which basically means it solves a problem, then it stops, checks its own work, learns from its mistakes, and then tries again. It just keeps looping, getting a little better each time.
And this chart just lays it all out, plain and simple. On one side, you've got HRM, bigger, two networks, all this complex theory behind it. And on the other side, TRM, almost 4 times smaller, just one simple network, and its whole idea is just this simple, powerful loop. No fancy theorems required.
So let's just walk through that loop because it's so intuitive. Step 1, it tries to find an answer. Step 2, it checks its own work. Step 3, it uses what it learned from that check to come up with a better answer. And then step 4, it just does it all over again. It's almost like a master craftsman, patiently sanding a piece of wood, making it smoother and more perfect with every single pass. Okay, so we have this tiny, elegant model. It's a fantastic idea on paper, but does it actually work? Well, let's get to the results, because honestly, they're absolutely stunning.
First, let's just let this number sink in again. 7 million. The TRM that pulled off these results has only 7 million parameters. That is just, it's a tiny, tiny fraction of what these giant commercial models are working with. And here it is, the punchline, this chart. Wow, this chart says everything. Look at that first bar. That's the giant LLMs. That's their big 0% score on those tough Sudoku puzzles. Okay, now, the middle bar, that's the complicated HRM model, gets a respectable 55%. But then, look all the way to the right. Our little TRM scores an incredible 87%. It doesn't just beat them, it absolutely crushes them. Let me just put that in perspective for you. This tiny little model is outperforming systems that have more than 10,000 times its parameters. That is just an insane level of efficiency.
So look, this is way more than just a cool party trick on a few puzzles. This has some major implications for the entire future of AI. So, what's the big takeaway here? What should we learn from this? Well, the main thing is that clever design can totally trump brute force. This shows we can get unbelievable performance with way, way fewer resources. And that right there opens up all these new, exciting paths for AI research that aren't just about let's build it bigger.
And you know what I love about this? Even the researchers who built it are saying, hey, we're still figuring this out. They think this recursive trick works so well because it stops a model from overfitting. Now, overfitting, think of it like a student who just memorizes the answers for a test. Sure, they might ace that specific test, but ask them a slightly different question, they're lost. They didn't actually learn the material. This tiny model, though, it seems like it's actually learning the logic.
And that just leaves us with one final big question. For years, the race has been all about building the biggest, most powerful AI. But this proves that sometimes the biggest breakthroughs don't come from thinking bigger. They come from thinking smarter and smaller. So you have to wonder, what other impossible problems are out there just waiting for us to take that lesson to heart?